This is Section 2, General Features of Sensory and Motor Systems. Before proceeding to specific discussions about the major sensory and motor systems, some common organizational features will be considered. Although the details of each system will vary, these features can be appreciated as a set of recurring themes throughout neurophysiology. Let's discuss synaptic relays. The simplest synapses are one-to-one connections consisting of a presynaptic element, for example a motor neuron, and a postsynaptic element, such as skeletal muscle fiber. In the nervous system, however, many synapses are more complicated and use synapses in relay nuclei to integrate converging information. Relay nuclei are found throughout the central nervous system, but they are especially prominent in the thalamus. Relay nuclei contain several different types of neurons, including local interneurons and projection neurons. The projection neurons extend long axons out of the nuclei to synapse in other relay nuclei or in the cerebral cortex. Almost all information going to and coming from the cerebral cortex is processed in thalamic relay nuclei. Topographical organization. One of the striking features of sensory and motor systems is that the information is encoded in neural maps. For example, in the somatosensory system, a somatotopic map is formed by an array of neurons that receive information from and send information to specific locations in the body. The topographic coding is preserved at each level of the nervous system, even as high as the cerebral cortex itself. Thus, in the somatosensory system, the topographic information is represented as a sensory homunculus or map in the cerebral cortex. See Figure 3-11. In the visual system, the topographic representation is called retinotopic. In the auditory system, it is called tonotopic, and so forth. Almost all sensory and motor pathways are bilaterally symmetric, and information crosses, or decussates, from one side, ipsilateral, to the other side, contralateral, of the brain or spinal cord. Thus, sensory activity on one side of the body is relayed to the contralateral cerebral hemisphere. Likewise, motor activity on one side of the body is controlled by the contralateral cerebral hemisphere. All pathways do not cross at the same level of the central nervous system. Some pathways cross in the spinal cord, for example pain, and many cross within the brainstem. These crossings are called decussations. Areas of the brain that contain only decussating axons are called commissures. For example, the corpus callosum is the commissure connecting the two cerebral hemispheres. Some systems are mixed, having both crossed and uncrossed pathways. For example, in the visual system, half of the axons from each retina cross to the contralateral side, and half remain ipsilateral. Visual fibers that cross do so in the optic chiasm. Let's talk about types of nerve fibers. Nerve fibers are classified according to their conduction velocity, which depends on the size of the fibers and the presence or absence of myelination. The effects of fiber diameter and myelination on conduction velocity are explained in Chapter 1. Briefly, the larger the fiber, the higher the conduction velocity. Conduction velocity is also increased by the presence of a myelin sheath around the nerve fiber. Think of the myelin sheath as the insulation around a copper wire. Without the myelin sheath, the insulation is gone, and the copper wire conducts much more slowly. Thus, large myelinated fibers have the fastest conduction velocities, and small, unmyelinated nerve fibers have the slowest conduction velocities. Two classification systems, which are based on differences in conduction velocity, are used. The first system, described by Erlanger and Gasser, applies to both sensory afferent and motor efferent nerve fibers and uses a lettered nomenclature of A, B, and C. The second system, described by Lloyd and Hunt, applies only to sensory nerve fibers and uses a Roman numeral nomenclature of 1, 2, 3, and 4. Table 3-1 provides a summary of nerve fiber types within each classification, examples of each type, information about fiber diameter and conduction velocity, and whether or not the fibers are myelinated or unmyelinated. This is Table 3-1, which demonstrates classification of the nerve fibers. As you can see, the type of nerve fiber can be A alpha, A beta, A gamma, A delta, B, or C. This goes in order from largest to smallest in diameter. It also goes in order from fastest to slowest. It also goes in order from myelination, which is all nerve fibers except type C, which has no myelination. In the first column is the type of nerve fiber, and the second column is an example of types of neurons and types of sensory information that is conducted by each nerve fiber. Table 3-1 here demonstrates the Roman numeral classification: 1A, 1B, 2, 3, and 4. Again, it goes from largest diameter to smallest diameter, as well as fastest conduction to slowest conduction. And again, the first three, type 1A and 1B, 2 and 3 are all myelinated, and type 4 fibers are unmyelinated. And again, the first column is the fiber type, second column gives you an example of the use of these nerves within the peripheral nervous system, and the type of information that is conducted by each nerve type. This concludes the section on further details of the motor and sensory nervous system.